How fast does a launch star launch you in Super Mario Galaxy? This is something I recently thought of and wanted to solve. And as it turns out, the answer is a bit more complicated than just X number miles per hour. So to figure this out, we need to calculate the distance Mario travels over the course of 1 second of flight. Then we can take that number and multiply it by Mario's height to get his rate of speed over the course of that second. From there, we can keep multiplying by 60 to find his miles per minute and then miles per hour. So without any further delay, let's go figure out some numbers. Mario's height is difficult to pinpoint without an official source, but it's commonly estimated to be around 5'1", so we'll use that. As a decimal, this is 5.083 repeating. Now, finding out how fast he's going is the actual hard part. First, I chose this launch star in Dusty Dune Galaxy since the camera angle makes it easy to tell what's going on. Then, I painstakingly made 60 cutouts of Mario for every frame and animated them along his flight path, essentially making an onion skin of his movement. In the clip, Mario passes himself about 90 times. 90 Marios with a height of 5.083 feet equals 457.5 feet per second, which multiplied by 60 is 27,450 feet per minute. To convert this into miles, we'll divide by 5280 to get roughly 5.2 miles per minute. And finally, to get our miles per hour, we'll multiply this by 60 one last time to get a top speed of around 312 miles per hour. So after all the math is said and done, 312 miles per hour is the speed for every launch star in the game. Or is it? Well, not every launch star propels you at the same speed. In fact, there's a few launch stars that seem awfully slow compared to others, especially the ones where you're traveling across a shorter distance. So that got me thinking, is the speed of a launch star directly related to the distance it launches you? This question started as more of a broad hypothesis, but then I came across arguably one of the slowest launches in the game, which, according to said hypothesis, meant the distance should also be extremely short. And it was. This turned my question into more of a theory that I wanted to prove, that there is a relation between distance and speed in a launch star. What is that relation? Well, that's what we're about to solve. To figure this out, I decided to calculate how many Marios passed during 1 second of this launch, giving us roughly 18 Marios per second. Using this, we can do the same math as before. Multiply 18 by his height to get 91.5 feet per second, and multiply that by 60 to get 5,490 feet per minute. Divide this by 5280 to get a little over a mile per minute, and multiply it by 60 one last time to get a final speed of 62 miles per hour. So now we have the speeds for each respective launch star. And now that we have the speeds, we can calculate how far they both launch you by timing the length of the flight and then multiplying it by our feet per second. The first star has you flying for pretty much 5 seconds flat. Earlier we established that Mario flies at a speed of 457.5 feet per second in this clip. And if we multiply that by our 5 seconds, we get a distance of 2,292 feet, which is just less than half a mile. So if you get launched a distance of 0.4 miles, in theory, you'll always go 312 miles an hour. But what if you get launched a shorter distance? Well, it's time to do the math on our other star. This one had us flying through the air for only 2 seconds. Multiply this by the 91.5 feet per second we got earlier to get 183 feet, which is only 0.03 miles, which means that's the distance you need to travel to go 62 miles per hour. So we finally have the distance to speed ratio between both of our launch stars. But now what? Well, I decided to make a chart to map out these ratios. Now that we have at least 2 different speeds and distances, we can fill out the rest of the chart. The distance between these two numbers is 0.399, which means the next distance in the sequence should be 0.833, assuming the increments we're going up by remain constant. Now, we could keep adding this number over and over again, but that's a lot of work that I don't want to do. Instead, we're revisiting slope-intercept formula. If we imagine these two ratios as points on a graph, we can easily map out a line that goes straight through them. This also means we can pick and choose any point on that graph and find the distance to speed ratio, regardless if it's by increments of 0.399 like before. But before we use y equals mx plus b, we need to figure out m, which uses the slope formula. Plugging our numbers into this formula gives us 625.4. We can use this as m and our other numbers for x and y to solve for b, which gives us 40.49. And now our equation for the slope that passes through both of our points reads as follows. Y equals 625.4x plus 40.49. Using this, we can find out the speed Mario is going for any given distance, which means, in theory, there's a distance far enough in which Mario's speed would have to equal the speed of light. And we already have the equation to figure this out. So that's what we're going to solve next. The speed of light is 670 million miles per hour, which we'll plug into the y value since y is our speed. Solve out the equation and we should get a distance of 1,072,000 miles. To put that into perspective, that's about 1/86th the distance from the Earth to the Sun, which compared to the size of our galaxy or even the universe is really small. Now we could break the universal speed laws and go faster than the speed of light, since Mario doesn't exactly follow any scientific laws in any of his games. But instead of trying to go even faster, I decided to look at the minimum speed you can go. According to our equation on the graph, the y-intercept is 40.49, at which our distance value is 0, which doesn't seem right. Traveling 0 distance means you're going 40 miles an hour? And if you wanted to go less than 40 miles an hour, you'd be going negative distance? So that got me thinking, what if our ratios weren't linear at all? What if the graph was curved? This would mean the graph starts at 0, 0, but still passes through both of our points, making it much more realistic. The formula for this is y equals a times x to the power of p. To find out the equation, put the numbers from the first launch into x and y and solve for p by dividing it by our second set of numbers. The a's cancel out and we're left with this, which we can then take the natural log of both sides so we can divide these numbers to get p by itself, which equals 0.639. Lastly, we'll put this number back into the formula again to solve for a, which is 531.8. This brings our final equation to this. Y equals 531.87 times x to the power of 0.639. Now, if we want to find the distance equal to the speed of light again, we just need to plug the speed of light into y. Solving this gives us a massive distance of 3.5 billion miles. And we got all that information from just 2 launch stars. Thank you all for watching. This video was a lot of work, but also a lot of fun. Make sure you check out all the links in the description to catch my posts on other platforms and to become a member of the K.A.R. crew. Subscribe if you'd like to see more of this type of content. I hope you enjoyed this video, and until next time, peace.